Cosine similarity offers a way to compare two vectors by focusing solely on their orientation, irrespective of their magnitude. To grasp this concept, it's essential to first understand what a vector is and the kind of space these vectors inhabit. A vector is essentially an ordered list of numbers, such as 2, 1, 3. Visualize it as an arrow in space. The arrow's length indicates the vector's magnitude, while its direction specifies how its components are arranged relative to each other. An inner product space provides a framework where vectors are equipped with an additional rule, termed an inner product, enabling meaningful comparisons between them. The inner product takes two vectors as input and yields a single number, capturing the extent to which the vectors point in the same direction. In familiar three-dimensional space, this inner product corresponds to the dot product, which involves multiplying corresponding components and summing the results. With an inner product defined, we can establish two fundamental geometric concepts: the length of a vector and the angle between two vectors. The length is derived from taking the inner product of a vector with itself. The inner product indicates whether vectors align in similar directions, oppose each other, or exhibit no directional relationship. Cosine similarity leverages this very idea by measuring the cosine of the angle between two vectors. When vectors point in the same direction, the angle between them is 0, and the cosine similarity is 1. When they are perpendicular, indicating no directional alignment, the cosine similarity is 0. Conversely, when they point in opposite directions, the cosine similarity is -1. We thus derive the cosine similarity formula from first principles using the law of cosines. Consider the vectors a and b placed tail to tail at the origin. Together with the vector a minus b, they form a triangle whose side lengths are given by the magnitudes of a, b, and a minus b. Applying the law of cosines gives one expression for the squared length of a minus b in terms of the magnitudes of a and b and the angle between them. Now we look at the same squared length from an algebraic perspective. Writing a minus b as a dot product with itself and expanding leads to an expression involving the magnitudes of a and b and their dot product. Since both approaches describe the same quantity, we can set them equal. The squared magnitude terms cancel, leaving a direct relationship between the dot product and the angle between the vectors. Dividing and rearranging then gives the cosine similarity formula, showing that it follows directly from basic geometry and the definition of the dot product. Now that this expression has been derived, we take it as a definition. We define the cosine similarity between two non-zero vectors a and b, denoted SC of a and b, as the dot product of the vectors divided by the product of their magnitudes. By construction, this quantity is exactly the cosine of the angle between the two vectors, so it provides a direct numerical measure of how closely their directions align. To understand what this definition is actually computing, we expand the dot product in component form. Writing a and b in terms of their coordinates, the dot product becomes a sum over dimensions, where each term multiplies the corresponding components of a and b and then adds the result across all indices. The magnitudes in the denominator expand in a similar way, as square roots of sums of squared components. Substituting these expressions into the definitions shows that cosine similarity compares the component-wise overlap of the two vectors, while the normalization by their lengths removes any dependence on overall scale. What remains is a purely directional measure of similarity that depends only on how the vectors are oriented relative to one another. The geometric intuition behind cosine similarity is straightforward. Think of each vector as an arrow from the origin in n-dimensional space. Cosine similarity compares only the orientation of these arrows, completely ignoring their length. This orientation-focused view has an important consequence. Scaling a vector by any positive constant does not change its cosine similarity with other vectors. For example, a vector a and a scaled version, say 3 times a, are considered maximally similar with cosine similarity equal to 1 because they lie on the exact same line through the origin. This property is called scale invariance, and it makes cosine similarity especially powerful for comparing objects where absolute magnitudes are arbitrary. Consider text analysis. A long document and a short document about the same topic may have very different word counts, giving them different vector magnitudes, but their direction and term frequency space could be identical, yielding a high cosine similarity that correctly indicates similar content. Let us work through a numerical example. Consider two four-dimensional vectors. X equals the vector 3, 2, 0, 5, and the vector y equals 1, 0, 0, 0. These could represent term frequencies in two documents. The first step is to compute their dot product. X dot y is thus computed below as follows. Only the first components contribute to our final value, since y has zeros elsewhere. The second step is to compute the norms. For x, we take the square root of the sum of the squared components, which gives a magnitude of approximately 6.16. For y, the same process applies, but since only one component is non-zero, the magnitude is simply 1. The third step is to compute the cosine similarity. We take the dot product of x and y and divide it by the product of their magnitudes. This gives a value of around 0.49, meaning the two vectors are roughly 49% similar in direction. This 49% similarity is moderate. Because y has a non-zero value only in the first dimension, the result reflects that x also points partly in that same direction, but not entirely. Some of x aligns with y, while the rest lies in other dimensions that y does not share. If x was the vector 3, 0, 0, 0, pointing exactly in the direction of y, the cosine similarity would be 1. On the other hand, if x had no component in common with y in that first coordinate, for example, if it were the vector 0, 2, 4, 1, then the dot product would be 0 and the cosine similarity would also be 0. We can also convert this into a measure of dissimilarity. A common choice is cosine distance, defined as 1 minus the cosine similarity. In this example, that gives a value of 0.51, meaning x is 51% distant from y on a scale from 0 to 1. Thank you for watching. We hope this video provided a clear and intuitive explanation of cosine similarity. If you found this helpful, please subscribe to our channel for more content on related topics. Your support helps us create more in-depth educational material. You can also support us on Patreon, where you can suggest future video topics, ask questions directly, and receive early access to new content.